Okay, a 15-foot ladder is leaning against a building, so here is the ground, here is the wall of a building, and here in blue is our 15-foot ladder. Its length is always 15 feet, no matter what happens to it. And it begins to slide out from the wall. So what's good about the ground and about walls is that they typically form 90-degree angles, which means there's a right triangle here. Now that means we can invoke the Pythagorean theorem anytime we want to. This distance x is the distance from the wall out to the foot of the ladder. And we have a distance y, which is the distance from the ground up to the top of the ladder. And it is always true that, according to the Pythagorean theorem, x squared plus y squared has to come out to 15 squared. The length of the ladder is fixed. And now they're saying that x is changing as the ladder slides outward. So the ladder is going to do that, and then it's going to do that, and it's going to do that, and eventually it's going to just crash to the floor, ground. And so we can track its motion just using the Pythagorean theorem, it turns out. So let's get this over here and let's do some calculus to it. What they're saying when the ladder slides away from the wall at 2.5 feet per second is that x is changing at that rate. dx dt, the rate at which x is changing with time, is positive 2.5. X is going up by 2.5 feet every second. And we can use that to find what they're asking for is at what rate the ladder is sliding down the wall, meaning how fast is y changing. So they're giving us dx dt, and they're asking us to find dy dt, the rate of change of the height. Well, we can get that if we differentiate this equation. If we do its derivative now implicitly, we get 2x dx plus, for the next term, we get 2y dy. And 15 squared is 225, but it's a constant, so its derivative is 0 no matter how big it is. So that's our differentiated equation. And then if we divide the whole works by dt, that by dt, 0 over dt is still 0, so I'm not even going to bother on the right side. This is looking good. This is something we can solve. I'm going to divide it all by 2 just because I can. It'll tidy it up slightly. X dx dt plus y dy dt must come out to 0. Now, how much of this stuff do we actually know? They're saying, at what rate is the ladder sliding down the wall when the top of the ladder is 3 feet from the floor? So this means y is 3. So we've got our 3 here. We want to find dy dt. So that's unknown for the moment. dx dt is 2.5. And x is, uh-oh, they didn't give us x. But we can find it because our trusty formula here is all set up. We know y. We should be able to solve for x in this thing. So quick pause, grab a napkin or the back of an envelope, and we can do x squared plus, they said y is 3, equals 15 squared. X squared plus 9 equals 225. X squared must be 216. So x must be 6 root 6, I think, but 14.7 pretty much, according to the calculator. Okay, so if we have a value for x, 14.7, we can put that in here. And now with a little bit of number crunching, we can find dy dt. dy dt should be 14.7 times 2.5. It's negative when we take it to the other side. We divide by 3. I get that dy dt is negative 12.24. And because it's y over t, it's a y value over time, it should be feet over seconds. So the top of the ladder is dropping at 12.24 feet per second when it's only 3 feet off the floor. Fair enough. Then they ask for another piece which requires some of our trig skills because they're talking about an angle now. So let's clear some space and try this some more. I don't think we'll need the Pythagorean stuff anymore. Now they're talking about the angle formed by the ladder and the floor. So here's the ladder, here's the floor. That's the angle they're talking about, the angle between. I will call that angle theta. And they want to know how it's decreasing when the base of the ladder is 10 feet from the wall. Well, looking at these two sides that form the angle, this, in trig mode now, I would call the adjacent side. And this 15, I would call the hypotenuse. Which trig function does adjacent and hypotenuse? That's a over h, that would be cosine. So we can say cosine theta equals adjacent over hypotenuse, which means it's x over 15. Or if you want to write 1/15 x, I'm actually going to do that. We'll go with x over 15, that's okay. Or if you want to say this, that would also work. What they're asking for is at what rate is the angle decreasing, which means they want to know about d theta dt. They want to know how fast, what change in angle do we get when time changes by 1 second. We can get that out of here. Now, when I learned these, I used to tie myself in knots trying to solve these things for theta, which is actually kind of hard to do. You end up using inverse trig functions, and it's no fun at all. It's not even necessary. All you need is an expression that has theta in it, and then you differentiate it, and let's see what happens. The derivative of a cosine is negative sine, so the derivative for this is negative sine theta, and then don't forget your chain rule, d theta pops out here. On this side, when you do the derivative, you get 1 times 1/15 x to the 0, so all that survives on this side is 1/15, and dx pops out on this side. Divide both sides by dt. And now we have a rate equation. This d theta dt is the thing they're asking us to solve. So we must isolate this. dx dt, we've already been given, it's 2.5. That's how fast x is increasing. So we want d theta dt, and that is 1/15. We're going to divide both sides of this by negative sine theta, so you end up getting this kind of awkward looking thing. Okay, there's the negative, and then we divided by sine, so I put it in the denominator, and then we have dx dt. Can we solve that? Probably. -1/15 sine theta. What is sine theta here? We need, you know what, they've changed the positions here, so we can't trust these numbers. I'm going to draw this diagram again. Sorry, I should probably have done this at the beginning, but here is our floor. Here is our wall. And for this question, they're saying the base of the ladder is 10 feet out from the wall. So our ladder is more like that. It's still 15 feet long. X is 10. This side is going to be 15 squared minus 10 squared is 225 minus 100 is 125, and the square root of 125 is 11.18, 11.2 we'll say. Okay, so there's the new situation. They've got the ladder in a different place. Sine theta is opposite over hypotenuse, so it's 11.2 over 15, which is 0.75. That's our sine value. There are about half a dozen other ways I could have gotten that sine value. I did that one just because I had to draw this. I wanted to draw this diagram anyway, and so I thought this made some sense. If you've got another system and it comes up with 0.75, then terrific, it worked. If you're having any trouble getting that sine value, get a hold of your instructor. They will be happy to talk about it. So -1/15 sine theta, and dx dt apparently is still 2.5 feet per second. So that whole cluster is our d theta dt. So it's -1 divided by 15, also divided by 0.75, and then multiplied by 2.5. And from that I get negative 0.2 repeating. And the units would be, it's d theta dt, so it's angle units over time units, so it would be radians per second. Angles are always in radians, not degrees in calculus, unless we specifically say otherwise. So pretty much always radians.